A very good morning to all of you, dear students of BSc third. So in this semester 5, as per Shivaji University, Kolhapur, syllabus distribution for the CBCS pattern is concerned, paper number 11, that is organic chemistry, is to be studied in this semester. So as far as this paper is concerned, paper is comprising entire spectroscopic study. So it deals with 5 spectroscopic methods. In that, unit number 1 is Introduction to Spectroscopy. Second one, important unit is UV visible spectroscopy. Third one is infrared spectroscopy. Fourth one, spectroscopic technique is proton NMR spectroscopy. Fifth one is mass spectrometry. And when we all study these concepts, lastly, we will discuss in topic number 6, that is combined spectroscopic problems. So this is a very interesting paper in your chemistry syllabus. Why? Because it includes so many concepts, and these concepts are very interesting one. So as far as spectroscopic methods are concerned, first we must know what is meant by spectroscopy. Very simple term. So it is the branch of science that deals with interaction of matter with light. So matter may be solid, liquid or gas. And when it interacts with light energy, what sorts of changes are taking place? That is to be studied by means of spectroscopy. Or we may alternatively define spectroscopy as study of interaction of electromagnetic radiation with matter. So now, instead of light word, I use electromagnetic, meaning that radiation which is having electrical component as well as magnetic component in it. So, what sorts of study and what sort of information that we are gathering from this spectroscopic study is very important one. So, in that particular scenario, we may now start with our basic understanding of spectroscopy. So this is nothing but principles of spectroscopy. So in particularly, it is based on the measurement of spectrum of sample containing atoms or molecules. So what happens in this? We are getting the graph. That graph is nothing but intensity of light absorbed or emitted versus frequency or wavelength. And this is nothing but the spectrum. So spectrum which is obtained after irradiation or after interaction of radiation with matter is in the form of graph always. And how it is measured? It is measured with the help of instrument which is called as spectrometer. And that spectrometer instruments differ from radiation to radiation. So there are so many number of spectrometers available in the market in order to measure this intensity of light absorbed or emitted or scattered. Okay. So we may define, or now we may study the types of spectroscopy. या ठिकाणी कोणत्या टाईपच्या स्पेक्ट्रोस्कोपी या ठिकाणी उपलब्ध असतील. तर ज्या वेळेला एखादं रेडिएशन हे ऍब्सॉर्ब केलं जाईल, त्यावेळेचा जो स्टडी असेल त्याला आपण काय म्हणतोय, पहिला पार्ट आहे ऍब्सॉर्प्शन स्पेक्ट्रोस्कोपी. तर या ठिकाणी अनालिटिकल टेक्निक which deals with measurement of absorption of electromagnetic radiation is nothing but absorption spectroscopy. For example, या ठिकाणी UV लाईट किंवा विजिबल लाईट तिच्यांना कॅरेक्टरिस्टिक वेव्हलेंथ आहे 185 ते 400 नॅनोमीटर ही UV साठीची रेंज असेल आणि 400 ते 800 नॅनोमीटर ही विजिबल ची रेंज आहे. ती ज्यावेळेला इंटरॅक्ट होईल त्यावेळेला आपल्याला ऍब्सॉर्प्शन मिळेल. मॉलिक्यूल मध्ये किंवा आयआर स्पेक्ट्रोस्कोपी मध्ये ज्या वेळेला 0.76 to 15 मायक्रोमीटरची रेडिएशन इंटरॅक्ट होती त्यावेळेला तुमचा जो स्पेक्ट्रम मिळेल तो असेल absorption spectrum, and that's why it is called as absorption spectroscopy. Then second type is emission spectroscopy, which is reverse to absorption, meaning that when light is emitted by the particle or by the molecule or by radiation dispersed according to the properties of that atom or molecule, and that is actually measured in this emission spectroscopy. So a very simple example is mass spectroscopy. In that, we will discuss different types of positive ions that are displaced and reflected from the ion source. So, this is a very important concept that we must know what is electromagnetic radiation and how it interacts with the matter. So, matter may be solid, liquid, or gas. Electromagnetic radiation may consist of electrical and magnetic components. So, accordingly, what sorts of changes that are taking place after interaction? That is our actual exercise. Okay. So, what happens after absorption of this radiation in the molecular or atomic level? Electronic energy levels are less. So, at room temperature, molecules tries to remain present at lowest energy level, that is E0. So, by absorption, what happens? That molecule get excite its outermost bound electron or lone pair electron, which is freely available, and now it is transmitted or excited to higher energy level E1, E2, or En, and that is called as electronic transition. Okay, so what is difference between these two energy states? That is given by means of very simple equation, that is delta E is equal to H nu, where H is nothing but Planck's constant and nu is nothing but frequency of radiation. So it is a mere difference between these two states, En, meaning higher energy state minus energy of room temperature, that is lowest energy. And most prominently, value of n uh, starts from 1 to n number. And delta E always for electronic energy level is in the range of 35 kilocalorie to 71 kilocalorie per mole. Okay. So now second energy level type, which is affected by absorption of this electromagnetic radiation by the matter, is vibrational energy level. And these vibrational energy levels are having less energy than electronic energy level, meaning that they are having a very less gap in between them, and it is gap in the range of 0.1 to 10 kilocalorie per mole. So what happens when IR radiation is absorbed? Molecules are excited from one vibrational level to another vibrational level, and molecule vibrates at higher amplitude. Okay, so and that is nothing but vibrational transition. Third energy type is rotational energy levels, and these energy levels are very discrete and quantized. And they are having a very less energy gap in comparison with vibrational and electronic energy levels. Okay, so what happens here? They are having less spacing. Okay, and therefore, when we calculate the energy difference between these three energy states, that is electronic, vibrational, and rotational, energy may vary in this proportion. That is, electronic energy levels acquire more energy than vibrational and than rotational, meaning that rotational transition requires very less amount of energy in order to excite one rotation to another one, rather than your vibrational and electronic energy levels. Okay, so electromagnetic radiation, as the name itself indicates, we know that it is in the form of energy packet, which is called as photons. So electromagnetic radiation, or basically photon, is a discrete beam of energy. It is consisting of oscillating electrical field E and magnetic field M in the perpendicular direction to each other. Now let us have a look to this figure. So from this source, now this photon or electromagnetic wave is propagating in this direction. Okay, so this is called as direction of propagation. So when we draw this magnetic field of this photon, then it is in the form of one wave. Okay, so this is the magnetic component of that electromagnetic radiation. Now, when we draw this 90-degree rotating electrical field component, it is in the form of another wave. So when we combine these two waves, it is seen that they are placed at 90-degree direction and perpendicular to each other. So one can say that magnetic and electrical component of the electromagnetic radiation, they are always oscillating in the perpendicular fashion. Okay, so this is very important aspect of photonic or electromagnetic. Now, when we consider wave characteristic of this photon, one must know uh, its properties. So first one such property is the wavelength. So how you can define this wavelength? So wavelength is defined in the typical manner, that is your sine wave. So when I plot this sine wave, this is the direction of propagation. This is the direction of propagation. And this is the oscillation that it takes. That is nothing but amplitude. Okay. So when we take identical points on this wave boundary, then it may be successive crest or it may be successive troughs. Then that distance is nothing but wavelength. Okay. So how it is expressed? It is expressed in uh, different units depending upon the region in which we are utilizing this electromagnetic radiation. So for X-ray purpose, very famous unit is angstrom unit. So how it is related with meter unit? So 1 angstrom is equal to 10 raised to minus 10 meter. In ultraviolet visible region, nanometers unit is used, where 1 nanometer is equal to 10 raised to minus 9. So this is the nanotechnology nowadays, which utilizes nanometer radiations and study in the 10 raised to minus 9 meter part. When infrared radiation is used, micrometer unit is used, which is shortly abbreviated as mu m, and it is nothing but 1 micrometer is equal to 10 raised to 6 meter. Now, second property is wave frequency. So how we can define frequency? This is the typical sine waves in which one can say one crest and one trough comprises one cycle. Okay, so number of wavelength units that are passed through that are passed through uh, a point in the space per second. Very simple. So number of waves which are passing at this point in 1 second, that is nothing but its frequency. So it is expressed in cycles per second, which is also known as hertz, and more commonly megahertz unit is used for this purpose. And this is the simple equation which relates megahertz frequency with hertz frequency. That is 1 megahertz is equal to 10 raised to 6 CPS or 10 raised to 6 hertz. Now we have seen so far these two properties. We know that frequency and wavelength, they are interrelated with each other by means of the simple equation, that is frequency nu is equal to c by lambda, where c is nothing but velocity of light, which is a constant term actually, and therefore one may write here simple equation relating frequency is inversely related with wavelength. That is, smaller the lambda, greater will be the frequency, and vice versa. Now, third property of this wave characteristic is nothing but wave number. It is nothing but number of cycles or wavelengths per centimeter distance. It is expressed in 1 by lambda, meaning centimeter inverse, which is also known as Kaiser unit. And this Kaiser unit relates mu is equal to 1 by lambda. Okay. Now, fourth one such wave characteristic is amplitude, which is shortly abbreviated as small a. So, what is this amplitude? The maximum displacement of wave from x-axis, and it is nothing but height of that wave. Okay, so when we consider water waves, in the sea or ocean, maximum is the height at the time of, we can say, uh, during that sea. Okay, तर या ठिकाणी आपण ज्या वेळेला कोणताही एखाद्या वेव्हचा हाईट मोजत असतो त्यावेळेला ती हाईट काय सांगत असते तर ती त्याची अँप्लिट्यूड सांगत असते. मॅक्झिमम इज द हाईट. तर आपण सुनामी वेव्हज म्हणतो तर त्यावेळेला त्या वेव्हची जी हाईट असेल ती एकदम हायर अँप्लिट्यूडच्या वेव्हज या ठिकाणी पास होत असतात. तर हा वॉटर वेव्हच्या बाबतीतचा कन्सेप्ट आहे. तसंच तुम्ही कोणत्याही मीडियम मधून ती अँप्लिट्यूड जाते ते पण महत्वाचं आहे. त्यानंतर पाचवी टर्म आहे ती व्हेलॉसिटी. So how we can define velocity? It is the distance traveled by wave in 1 unit time. तर युनिट टाइम काय असू शकेल सेकंद असेल किंवा मिनिट असेल. तर इट इज कॉमनली एक्सप्रेस इन सेंटीमीटर पर सेकंद. आणि ही कोणत्या मीडियम मधून व्हेलॉसिटी किंवा रेडिएशन पास होतं त्याच्यावरती ते डिपेंड करेल. व्हॅक्यूम मध्ये व्हेलॉसिटी आपल्याला सर्वांना माहित आहे 3 × 10⁸ मीटर पर सेकंद किंवा 3 × 10⁻10 सेंटीमीटर पर सेकंद अशा पद्धतीचं हे युनिट असेल. आणि ते फ्रिक्वेन्सी आणि वेव्हलेंथ युनिटला C इज इक्वल टू न्यू म्हणजेच velocity is directly proportional to frequency. It is also directly proportional to wavelength. So that is to be uh, included. Now last energy parameter is nothing but energy of radiation. तर या ठिकाणी वेव्ह थेरी काय करते तर या ठिकाणी काही फिनॉमिना वेव्ह कॅरेक्टरिस्टिकचाच फक्त फिनॉमिना एक्सप्लेन करते. त्याचबरोबर आपला जो इमिशन किंवा ऍब्सॉर्प्शनचा फिनॉमिना आहे ऍज पर क्वांटम मेकॅनिक्स त्या ठिकाणी एक्सप्लेन केलं जातं. म्हणून त्या ठिकाणी आपण इलेक्ट्रोमॅग्नेटिक वेव्ह त्या पार्टिकल फॉर्म मध्ये आणि वेव्ह फॉर्म मध्ये पण आहे. म्हणजे ते ड्युअलिझम या ठिकाणी पार्टिकल वेव्ह पार्टिकल ड्युअलिझम असं आपण त्याला म्हणूयात की ही एनर्जी वेव्ह जी आहे ती एकतर पार्टिकल फॉर्म मध्ये पण आहे आणि वेव्ह फॉर्म मध्ये पण आहे. म्हणून अशा एनर्जीची जी पॅकेट आहे त्याला आपण काय म्हणतोय फोटॉन्स. ओके, सो फोटॉन्स आर एनर्जी पॅकेट्स whose wavelength and frequency as well as wave numbers are related by means of very simple equation, that is E is equal to h nu. Okay, so h nu, h stands for Planck constant. Its value is 6.63 into 10 raised to minus 34 joule per second, and nu is nothing but frequency. Now frequency is related to wavelength by means of very simple equation that we have seen earlier. So E is equal to hc by lambda. So when we relate this energy, E is equal to hc mu. So energy is directly proportional to velocity and wave number. So one can easily characterize the energy packets associated with the photon. It determines the intensity. So number of photons decides the intensity of beam. More the number of photons, greater will be the intensity of that beam or radiation. Okay. So energy units are always ergs or joule units. So one can put one simple equation for relating these two units. 1 joule is equal to 10 raised to 7 ergs. And very importantly, radiation or photon having identical wavelength, identical frequency, identical amplitude, identical energy are called as monochromatic radiation. So monochromatic radiation, as the name itself indicates, mona meaning that single, chroma meaning that color. So single color, same energy radiation is nothing but monochromatic radiation. And very simple and familiar example of this is the sodium vapor lamp, which is having constant lambda, constant frequency and constant energy that we are observing at our street lights. Okay, so these are the various wave characteristics that we have studied so far during this lecture. Okay, so in the next lecture we will discuss another part.